So when we're working in predicate logic, what we'd like to be able to do is use all of the Boolean inference rules that we've already got. So for example, we see here that we have P of Cam and Q of Brent, and we'd like to be able to use modus ponens on that and assert that therefore Cam and Brent are friends. The problem is that modus ponens is an inference rule, and it has to apply at the level of an entire logical expression. That's not what we've got here. We've got the expression inside the quantifiers. So we have the rules of instantiation and generalization that let us transform predicate logic expressions into Boolean ones so we can work with them and then transform them back if we need to. So let's see how that works in this case. We apply universal generalization to say, well, if this is true of all x, then in particular it must be true of Cam. And if it's true for all y, then in particular it must be true of Brent. And at that point then we can conclude that using modus ponens and the other two facts that we've got, that Cam and Brent are friends. Okay, so we have two quantifiers. We need two pairs of rules. In particular, we need for each of them an instantiation rule. The instantiation rule goes from a general claim to a specific one. So that's what we just did. We said, well, if the claim is true for all x and all y, then in particular it must be true of Cam and Brent. And we strip off the quantifiers and we get a Boolean expression. Now, in some cases, what we need is to go back the other way. After we reason, we'd like to be able to derive universal claim. So we have what we'll call the generalization rule. It goes from a specific case to a general one. So in case, for example, we had argued P of some arbitrary object, call it A1, and Q of some arbitrary object, call it A2, then, and suppose we were told that in that case A1 knows A2, then we ought to be able to argue that for all possible x's and y's, then x knows y. So that's our generalization rule. And of course, we need that for existential quantifiers as well. So we need a total of 4 rules. Let's look at them. So the first one is universal instantiation. This is the one we've just been using. If some predicate P is true of all x's, then it's true of any particular one, C, or whatever other one we would want. And going back the other way, if we've proven that P is true for some arbitrary value C, then we can infer that it must also be true of any value x. Similarly for the existential quantifier, if we know that there exists some value that possesses some property P, then fine, there is one. Call it C. Call it anything you want, as long as it's not some value you're asserting anything else about. We don't know which one it is. We just know that there is one. We'll give it a name. So we can substitute C for X. And the final rule says, well, if you know that P is true of some value C, then you can assert that there exists some X such that P is true. So those are our 4 rules. Notice that in order to use them, we have to go from the outside in as we peel them off. Look at the doll. Suppose that we tried to take the doll apart. Smallest dolls first won't work. The only way to take the doll apart is biggest ones first, these guys, then we get to these guys, and then we can go down in. Exactly what we're going to have to do when we apply our rules. So let's take an example. In this case, we're going to do it right, like the dolls. Okay, so for all x, there doesn't exist a y, so that x likes y. I'm sorry, for all x, it's not true that for all y, x likes y. So for everybody, there's something they don't like. All right, let's manipulate this expression using the rules correctly. We can generalize and take away the x, and we get that for, say, Alex, it's the case that he doesn't like everything, using universal instantiation. Now I want to do something to get rid of for all y, but remember that these rules are inference rules. You have to use them on entire expressions, and we can't do that right now because the for all is not at the beginning. So we'll use quantifier exchange, and we get there exists a y such that not this. That's fine. And now we can apply existential instantiation. But we have to be sort of careful here because this existential occurred inside the scope of this original knot. I'm sorry, of the original x, here, the particular value of y is a function of the particular x. There may be something Alex doesn't like and something that Casey doesn't like and so forth. It does not have to be the same thing. So recall that to handle that, we use Scullum functions. We say that for Alex, there is something, as a function of Alex, that is not like. All right, and this seems right. Follows from the original claim. There's something Alex doesn't like. Fine. Now let's see what happens if, on the other hand, we do it wrong. So we're going to start over. We have, for all x, it's not the case that everything is liked. Now let's do major surgery. What we're going to do here is reach down inside this expression and do a transplant. We're going to replace just the for all y likes xy using something we'll call questionable universal instantiation. And we'll replace the y with b. In this case, I'm going to pick an arbitrary value, not a particular value x, but an arbitrary one that I could reason with and perhaps derive universal conclusions later. So I have that. Everything else stays the same, just that. Okay, now let's do the next step. Let's use real universal instantiation now, and we can get rid of this guy. And we have not likes a, b. And a, again, is an arbitrary value. So now it's allowed, using the generalization rules, to put back quantifiers. Let's do it correctly. Universal generalization says, well, if it's true of an arbitrary value b, then it's true for all values b. So we get that. And let's do it again. And if it's true for an arbitrary value a, then it's true for all values a there. But look at what we've got. We've now asserted that nobody likes anything. That's not the same as our original claim, and it's not entailed by our original claim. Our original claim didn't say that nobody likes anything. So we've used an unsound inference rule, and we've derived something that's not entailed by the premise. That's a problem. We don't want rules that do that kind of thing. We've got junk.
Elaine, it's laundry day. Can you give me your socks, please?
Oh, okay, sure.
I'm not going to be washing your shoes. All I need is your socks.
Yeah, but, let's see, off with the other shoe. Off with the socks. There you go.
There's some glass on the floor. I think you should put your shoes back on.
Oh,
Maybe you want to put on a clean pair of socks.
Uh-huh. Yes. Excellent. Socks going on.